Hey y'all, welcome. We're going to go over our solutions to our test, and this is going to be the first exam problem that we had. So remember, we had this circular track. There was the guy on the skateboard going down that circular track, and his mass was 60 kilograms. And we were told that when theta is 0 degrees, which here is theta, theta just measures from this initial horizontal line here down to where the guy is. When that is 0 degrees, he's going to be at rest. All right, so the initial velocity for this problem is going to be 0. What we want to find is our normal force at when theta is 60 degrees. All right, so that's what we're looking for. Now, first thing you should do when you see this problem is realize we've got forces involved. I've got a normal force, I've got a weight, and we have a curved track. So curved track indicates normal acceleration. All right, so first let's draw our free body diagram. So let's just draw a box. It's going to represent our skateboarder. And we need our normal force because he's on a surface. What else do we have? We have weight. All right, so we have that. Now let's go ahead and label our axes. So the normal axis is always going to be pointing in towards the center of curvature. So let's go ahead and make this right here be the positive in axis. And then T is going to be perpendicular to that, and I always say that that is in the direction of motion. So that will be T, and this angle right here is theta. Okay, so now we've got that done. Next thing we want to do is sum up our forces. All right, so let's do the in direction first. Remember that that is the positive in. And if we do that, we're going to have a normal force here that's just positive, lies directly on the n-axis, so we just put plus n. And then I have a weight component. So the weight component is going to be going, in this negative direction. So we're going to put a negative mg for the weight, and then sine theta. All right, so we have that. I'll plug in the mass and gravity in just a minute. And then let's set it equal to the mass times the acceleration. But this is in the n direction, so we're going to have the normal acceleration. All right, so we have m times an. Okay, and then let's fill everything in here. All right, so n, I don't know what that is yet. That's what I'm looking for. And then we have minus the mass, which is 60 kilograms. And then we have gravity, so it's 9.81. It's meters per second squared. And then sine, let's leave that as a term of theta. And then that is going to equal our mass, which is 60, times v squared over rho. And what should rho be? It's going to be 4. All right, because of this right there. All right, so now we have this. Now, we've got some unknowns in here, right? So let's just go ahead and solve this for n, and then we'll hang on to it. So n is going to be 15 times v squared plus 588.6 times sine theta. So I already know what theta is going to be. It's going to be 60 degrees at the end, but I don't know what my velocity is going to be at that point. So I'm going to have to find that. All right, now let's go ahead and let's look at our tangential axis, and then we'll see if we can use that information to find t, or v, not t. All right, so in the tangential direction, we're going to have our weight component. All right, so it's positive. So it's going to be the mass, which is 60, times the 9.81, which is meters per second squared. This one, 60 is kilograms. And then we're going to have cosine theta. And then that has to equal the mass, which is 60, times your tangential acceleration, which right now I have no idea what that is. Okay, so what we need to do then is let's solve for AT. Now notice this mass terms here cancel. So we're going to have AT equals 9.81 cosine theta. Now, what are we going to do with that? Well, remember we've got this equation right here. Right, so this is an equation we used a long time ago. So we have v dv equals a ds. Okay, now this a in here, this is at. So remember, your normal acceleration does not go into these equations. So your kinematic equations does not use, none of those use an. All right, so it's always at. So let's go ahead and use this equation. Now you might be wondering, we have at, that's a function of theta. So what do we do with that? Well, remember, we can rewrite ds as r d theta from arc length. Right, so now I know what r is. It's 4. So we're going to put ds equals 4 d theta. So we're going to substitute this in for ds. All right, and then we're going to integrate both sides. All right, so I have the integral of v dv. My limits will be 0 to the final velocity v. And then the right side, I'm going to have at, which is 9.81 cosine theta, times ds, but ds is now 4d theta. All right, so we'll put 4d theta right here. And what do we think our limits should be? It's going to be limits of theta, so we're going to have 0, and then finally we're going to the angle of 60. So 0 to 60 will be our limits there. Now we just need to integrate. All right, so we're going to get v squared over 2, and then that is going to equal 39.24 sine theta, evaluate at 60 and 0. So once we do that, we're going to get that v squared over 2 is 33.98. So then v is 8.24. And that's meters per second. Okay, so this is the velocity of the skateboarder at 60 degrees. All right. Now, what do I do with that? Remember, we're looking for the normal force. Well, if we scroll back up here and we look right there, we've got an equation for the normal force that is a function of v. So we're just going to take this velocity, square it, and then we will be able to find n. All right, so n then is going to equal 15 times 8.24, square that, plus 588.6 times sine of 60, since I want the normal force of 60 degrees. Then with that, n is going to be 1,529.23 newtons. And that is your normal force when theta is 60 degrees. All right, so this problem used kinetics. It also used our old equation from our kinematics section. And there you have it. All right, guys, I'll see y'all for the next one.